Good morning again. I'm afraid we've had a change of speaker because we've unfortunately Kieran Morgan is he's not feeling very well, so he may turn up later. But in the meantime, we're going to change it to the beginner session. And I'm sorry if some of you already know about this, but it's going to be an entertaining event. I'm sure it will. And our presenter is Dr Heather Nickalls M0HMO. There you go, Heather. Thank you.
Thanks very much, guys. Okay, so I've given this talk in various versions a few times to the AMSAT colloquium, and what we've seen is that 3/4 of the audience already know everything I'm saying, but they're really interested in satellite stuff. So this time I'm going to have some audience participation. So all those people who know what they're talking about are going to get to answer some of the simple questions here. So hopefully it won't be completely boring for all those who've done it before. There we go. We're going to start at the very beginning. Anyone answer that question? What did the very first Oscar satellite send? Go on then. What? Hi. Yes. Even I could do that in Morse. So there we go. That was right. Okay. So here's a bit of background information. This picture is supposed to represent the ISS kind of orbit, and as in, does that work? Yes, 408 kilometers on average. And that's how far it is off the Earth. A lot of people think these things are miles and miles and miles away, but on the big picture like that one, that is what you will see. So now you can probably imagine that if you've got a satellite, it's somewhere around, it's only going to be seeing this bit of the Earth. So that's why the low Earth orbit satellites don't see very much. They're going round, they're not seeing a great deal. The NOAA satellites, the weather satellites, what does NOAA stand for? Oh, come on, this is an easy one. National Oceanic and Atmospheric Administration. Thank you very much. And ISS, come on, everybody. Yeah, thank you very much. Okay. So the ISS, it's sitting up here. Okay, it's 4 times the height of the atmosphere, but there's still stuff going on there, and it has to correct its position. Every now and again it drifts down, and then it does a bit of a burn, and it pushes itself up a bit. Why? Do we know that? Anybody know why? Classic answer, it's gravity. No, it's so. Some effects are because there is still atmosphere up there, but the other one is the solar winds. The solar winds are actually making quite a lot of pressure on the thing, and obviously when you try and slow it down, it tries to fall down to Earth. So, okay, so anyway, that was just a bit of background there. There's another picture. This is not a very good one, but it shows the ISS orbit relative to Everest, and you can just about make out the Mariana Trench there. So this sort of sets the scale. You're not in trouble when you're on the ISS of running into anything. Just for completeness, this is not around anymore, but some things do this. They go really close in, and then they go really far away. So these are very elliptical orbits, and of course they're difficult to find out where they are and so on. So, oops, sorry, there we go. Right, okay. And the last significant one is the geosynchronous orbits. So this is a satellite that it falls around the Earth at the same speed the Earth turns round, which means it doesn't move in the sky. You put it up there like your Astra satellites for anyone who does Sky TV. And they're a long further away. They're up at the 36-kilometre mark. So who's spotted what is wrong with this picture? Scale's about right, but this satellite is going around the poles. And geosynchronous orbits only go around the equator. So, but have you tried finding a picture of the Earth from the poles? It's very difficult. So anyway, there we go. So we've covered a little bit of the basics. Let's jump straight to the most complicated and difficult one to actually talk to, which is this geosynchronous satellite. So satellites are almost all called Oscar something. Oscar stands for Orbital Satellite Carrying Amateur Radio. And then this particular one is given the designation QO100, standing for Qatari Oscar. So it's an acronym within an acronym. We love that sort of thing. And it's also known as S-HALE, which is the name of the company in Qatar that put this thing up. But it's also the name of a star, and the star is Canopus. Okay, good. Anyway, so this is an interesting one. It goes up to the satellite on 2.4 gig, and it comes down from the satellite on 10 point something gig. So this isn't your Yagis, this isn't your backdoor kind of approach. This you're going to need some serious hardware for. But it's also probably the most entertaining and challenging of the satellites. So yes, working this thing is interesting. Okay, so here it is, geosynchronous orbit. Here's the Earth looking down from the North Pole, or onto the North Pole. Why do we have a picture of a bird? Because everybody in amateur radio or satellite world calls them the birds. So, and it's much nicer to have a picture of a bird on the screen than it is little bits of metal. Anyway, so this one is at 25.9 degrees east. And so I have seen people saying, oh, I pointed my dish at 25.9 degrees and I couldn't hear it. Well, it only works if you're living at the North Pole. Hands up everyone who lives at the North Pole. Not many of us, right? So if you're, for instance, around here, which is at 25.9 degrees east longitude, then you will see the thing in a completely different place in the sky as if you're on the zero, the meridian where we are, roughly. So that's the first problem, that just because they tell you that doesn't mean you could just point at that. It means you have to work out where it is in the sky relative to where you are on the planet. And here's an example. If you're actually sitting here and it's a very close-in satellite, you would be looking almost horizontally at it. Whereas if you're on the North Pole, you're looking obviously across at it. So it depends on its distance away and on where you are on the Earth relative to where the satellite is. Because remember, the satellite doesn't move relative to the Earth. And it gets worse because you've got to look at the elevation. And so if you now look at it north and south, if it's a long way away over here, then as you see it on the Earth, which is roughly where we are, it will be at a different angle. If it was really close, it would be at another angle. So there's a lot of spherical trig. Does anybody remember the spherical trig from that far away? There's one or two people nodding. That's impressive. I can't. But it gets worse because hopefully you're all familiar with horizontal and vertical polarization of antennas. This matters as well. So if you're right underneath it and it's over here, then it's going to be horizontal as I've drawn it here. But if it's further round this curve, which is, what's it called? Clarke belt. Arthur C. Clarke, the guy, the author who first proposed it. So this is the Clarke belt. All the satellites are round the Earth, and they form obviously a circle. And wherever you are on the planet, you will probably see something like this. So all the satellites are dotted around there. So you've got your Astras around here. This is Oscar 100 at 25. But if you're looking at one round here, you can see that it's not horizontal anymore. It's at 45 degrees or something like that. So not only have you got to get your trig to work out where it is in elevation and in azimuth, in the angle, you've also got to work out how much to turn your antenna in order to get it to point to the right. It's all very, very complicated. It's a lot of spherical trig, but you could just use a website. There's plenty of them. This one, you tell it where you are, and you tell it where the satellite is, and it gives you all the numbers. There are 2 bearings. Why are there 2 bearings? Somebody who knows about these things, come on. I'm not getting a lot of audience participation here. Okay, so north is not necessarily north. North depends on whether you're actually using the planet north up here, or whether you're actually using a compass which is pointing slightly off north over here somewhere at the moment. So you'll be using a compass if you're setting this all up, so use the compass one. It tells you the elevation, it tells you the skew, that's the angle to turn the... so this is telling you that you should turn it minus 19 degrees clockwise, i.e. 19 degrees anti-clockwise. And it tells you the elevation as well, so even though it's at this angle, you should point your compass at this angle if you're here, and you should have the elevation at that. But now you should have enough to set up a tripod, set something up on the side of your house, and go and point it in the right direction. And this is the same process that your astro engineer or whatever will install your sky dish. That's exactly what they're doing. They work out where you are, where they should point it, and then they put the dish up and set all these parameters. So, and remember, this is the complicated one, okay? It gets easier from here. So what does it give you? Well, receiving it is quite easy. We'll talk a little bit about what you can receive. Basically, you're probably going to want to use a dish, although it can be done with a little feed horn, which is a little bit specialist, but yeah, dishes are the way to go, really. You can receive it with these little blue SDRs. I haven't got one here, but I'll show you a pic later. And also, you probably noticed that this thing transmits TV pictures. And if you've got a TV picture coming down, you're going to need some specialist hardware to receive it, which is this thing called the mini tuner, available from the BATC. They've still got lots of them available. The nice little kit to build up. Thank you very much, John. So these are, yeah, this is the kind of thing. You've probably all seen these little SDRs. They do 28 meg to 1.2 gig or something. And they'll receive Oscar 100 quite nicely for the narrowband. And this mini tuner thing will do the rest. You're going to need an LNB. We'll talk a little bit more about those in a minute. And you're going to need a bias T. If you're familiar with bias Ts, it just puts a voltage in that will then power the LNB. Same as you've got on your satellite dish. You've got this little lumpy thing that kind of probably looks a bit like this bit without the green stuff. Yeah, and what computer software? Well, anything will do. Laptops look fine. If you want to do ATV, you're going to want a ports down. That does the transmitting, but it also does the receiving. Why have I highlighted Longmend? Because I wrote it, and I'm too modest to say, okay. And if you're going to do it on a PC, this guy, SDR console, it's a good bit of SDR software, but the great thing about it is that it can track movements in the frequency. So all these things are dependent on temperature. As the temperature changes, so the frequency might shift. If the frequency is going to shift, rather than you manually tuning all the time, this thing will actually track it. It's a bit complicated to set up, but it's well worth it. And it means you can use cheaper hardware. Okay, so we'll have a little bit talk about dishes. I realized when I was talking to some people recently about this that they didn't quite understand the difference between a center-fed and a offset-fed dish. Hopefully this describes it. This whole arc from the top here to the bottom is a center-fed dish. Parallel rays coming in from a long way away all get focused at one point. That's where you put your detector, your feed. That's this thing here. But also you could just have a bit, and here I've highlighted a bit, just that bit, which also, it's obviously a smaller area, but it is also focusing on a single point. So that's the dish. That's what an offset dish is, just a little bit of a full-size parabolic dish. The advantage of this offset dish is that nothing is getting in the way. When you've got one of these feed things here in the middle of your dish, it's getting in the way. Signals can't go through it. Whereas an offset dish like this one, you can see that actually most of the signals are going to come in here, missing your feed. Sorry, I'm not keeping the microphone in the right place. Okay, what feed LMBs? Well, any ones will do. An Astra TV one will do. But this one, the Bullseye, is nice because it has certain features which mean that it will lock. It's got a TCXO, which means basically the frequency is much better controlled than some of the old cheaper ones, the Astra ones. And you can see a picture there I've just found off somebody on the web. That's what it looks like underneath the cover or something similar. And if you cut the top bit off it, you end up with something that looks like this. Why do we do that? Because this diameter is pretty much the same as copper pipe that you get for water supplies in your house. And with the use of one of these rather scary looking gadgets, you can just expand it very slightly, put an expansion on the end. I don't think you can probably see that, but that's slightly expanded there. And then it will go over the end of that. And you want to do that if you ever want to transmit. So we'll come to that in a moment. So what do these things do, these LMBs? They don't demodulate all the way down to 0. You don't get audio out of them. What you get out of them is an IF. In this case, you can see the math. It's around about 740 megahertz. So the LMB basically subtracts 9.75 gigahertz. You get, sorry, yeah, that's a typo there. It should say 739 megahertz. If we're running at gigahertz, somebody's doing something very, very wrong. But very impressive, actually. Anyway, it comes out of these things. Then it goes down the cable at 75 ohm cable, just so that you don't get confused by these things. Most things don't. It doesn't really matter at that point, but worth bearing that in mind. So you're going to need a radio that can receive 739, which is going to be an SDR, basically. And that's where these guys come in again. This sort of little SDRs do a good job of that. So if you want to transmit, you may remember earlier we talked about transmitting on 2.4 gig. So you're going to need something that does that. You're also going to need a bigger dish because you're going to need a lot more power if you're going to do television. But we won't go into too much detail on that. Lots of ways of doing it. You could buy an up converter so that you transmit your normal radio on 70SEMS and it'll up convert to 2.4 gig. You can get transverters, which is kind of the same thing, or Plutos and Lime type SDRs, which will actually transmit at that 2.4 gig straight away, so you don't need anything in between. You will need some amplifiers. If you're going to do TV, you come back to this BATC product, the ports down, which will basically send TV pictures through a Pluto or a Lime. If you want to do narrowband and you're getting set up with a Raspberry Pi anyway, Colin Durbridge has done this program called Langstone, which again is part of ports down, so you can just get to it from ports down. And that will let you use a mic and speakers on connected to your Raspberry Pi. Or again, you can use SDR console program with a PC. You're going to need some amplifiers. 2.4 gig amplifiers are a little bit more specialist. We'll talk about those. Just to illustrate the point, he's not in the room. Mike is not in the room, is he? No. He's been around. He's here today. He's doing lots of things. But he designed this, and this is a remarkably good piece of design work. As I said, it's based on a bit of copper pipe. There's a is that a commercial one, John? Yeah. Right. So, yeah. So there's one. It's a patch antenna. It's got an SMA underneath it here, and it just connects into the end of one of these. If you're making one on your own, you can end up with something like that. You get a kit with a few bits of brass and a bit of tube, and you just put it all together. Actually quite easy to do. Not so easy. Yep, AMSAT shop. There we go. All done for you. A little bit harder to test if you've got antenna analyzers that can go up to 2.4 gig. So be it. Otherwise, yeah, plenty of people around who can help out. I said you're going to need amplifiers. If you're going to go for the sort of homebrew approach, this thing on the left is a Wi-Fi amplifier. It needs a little bit of modification so that it only transmits. But it's quite easy to do if you're okay with soldering onto a PCB. And that just does the job. And that, as long as you can feed it with enough of a signal, if you haven't got enough signal, the thing on the right, I think, what does it say? It costs £5. There we go. So they're probably a bit more than that now. Yeah, so bit of an amplifier chain with a Wi-Fi amplifier at the end, and that'll get you up to serious amount of power, enough to talk to the satellite and people will be able to hear you back on Earth. If you want to do TV, it's a bit more of a challenge because you need to know who's there and who you're receiving and all the settings they're using. Luckily, Phil, say hello, put together this thing which basically shows you everything that's going on and has a chat room, so you can go in there, see what people have said they're working, well, what their type of their signal is, and then you can type it all into that mini tuner program or whatever and see those signals. So it makes it really, really easy to know what's going on. This signal on the left is this really big one is a beacon. This is fairly well known. You'll probably see it downstairs in the AMSAT stand. This is basically just telling you all about the Oscar 100 and so on. But it's there as a video beacon so that if you can perceive that, you know you're set up, you're on the right frequencies and so on. Okay, so we've looked at the really hard one. Hopefully you got some idea of what you might need to do to receive that. Now we go to the easy ones, or middling ones anyway. The flying repeaters. These are basically, you talk to them on 2 or 70, they talk back to you on 70 or 2, so they're transcoding between the frequencies. And they fly overhead. They're mostly LEOs, so they're only 400 kilometers up or more. Yes, so you're basically, this is going to come over the horizon, you talk to people on it, and then it goes off the horizon again 10 minutes later. There's a lot of them. Some of these we've talked about already, so let's see, Oscar 100 is here, that's the narrowband bit of Oscar 100. You've got all these ones here, you've got the ISS, various modes that it does, and SO50 down here, which is my favourite one. And all the things in blue are basically where people have actually talked to it. I printed this out, I think Thursday. So there's a lot of them up there, and a lot of them are very active. So AMSAT.org/status, good place to go to find out what's there, what you can work. Any problems with it, it'll be reflected here, and then you can know you won't be able to work it or whatever. Okay, we talk very little bit about the fact that, as you can see on the right, there are the trace that the satellite makes over the planet is actually a circle, but it appears on maps, which are projections, obviously, from a sphere to a flat surface, as these sine waves, curvy waves. I brought this little globe in here. I very cleverly put an elastic band around it to show you how the orbit goes. So you can see the elastic band is pretty much going round a great circle, so shortest path. And this one is showing you that from the UK, which is here, if you want to work Australia, you have to point sort of northeast, which is counterintuitive. When you look at a map, you think it's southeast. But in reality, to work Australia, you start here and you go up over the north, just missing Norway, above Moscow, and then all the way down to Australia, which is that curve on the. So you would work Australia through a path that goes up here and down here. So anyway, that's why you get these weird curvy lines. And if you're trying to work satellites, you'll see a lot of those. The one on the left is the footprint of that Oscar 100. That's kind of what it can see. So because it's so much further away, it sees a lot more of the planet, and you actually get kind of a third of the planet onto that. And again, it's not circular because of the projections of the maps. Other places to find information. I like this website, N2YO. Again, it'll plot you a pretty picture of where things are. Here's the ISS a few days ago. But it'll also tell you when it's going to be visible above the horizon. So that one in orange there tells us that on the 18th, whatever that is, 7 days' time, there'll be a good pass where at 7 o'clock-ish in the morning, it will be up quite high in the elevate. John?
Let's just hope so, because we're actually talking to the space station on that day.
There we go. Yeah. We'll come to that in a moment. Lots and lots of good acronyms. Acquisition of signal, loss of signal, which is LOS, which is not line of sight, in case you're thinking in terms of terrestrial stuff. So, yeah, not only are they doing acronyms, but they're also reusing acronyms that we already know what they mean. Anyway, so now you've been on this website, you've got an idea of where the thing's going to go. You want to receive it. The one on the right there is a homebrew one. Kent Britton, who's not here today, but sometimes comes to the convention. He's got some plans to make one. I haven't brought mine in. I've been a bit of a familiar sight walking around with my piece of wood with bits of coat hanger stuck to it. And they do work. But if you want to fork out a little bit of money, this is an arrow antenna. Why is it called an arrow antenna, John? Yeah, because it's made from arrows, quite literally. So these aren't all that expensive. 100, 150, something like that will get you one of those. And the idea is that you can hold it, point it at the satellite, turn it round a bit to get the polarization for whatever it's in, follow it across the sky whilst talking to other people on the planet through that satellite. You can just see this little bit here. This is a diplexer because it's 2 and 70, so that means that you can combine them both into one coax, which you can connect to your handheld or whatever. Okay, we need to talk a little bit about Doppler. Have I got a volunteer who can tell me what it sounds like when something goes past you showing Doppler? Because I'm not going to do it. Does everyone know what Doppler is? Yeah, okay. That's a relief. Okay, so as it's coming towards you, it's going to be at a different frequency, higher frequency. When it's going away from you, it's going to be a lower frequency. The tradition, or I guess the default here, is that you transmit on the same frequency all the time, and the Doppler gets doubled, goes up, comes back down. So your receive frequency is the one that you want to adjust. The AMSAT recommendation here, this example for SO50, program up your handy with various presets, set it to where you're going to see it. So this is, in this case, channel 2. You're going to start on the high frequency, and then as it goes over the sky, comes towards you, then goes away from you. You just, every now and again, you're just going to click it to the next preset, which will have all these programmed in. You can get all this information from those websites we were looking at. And it is a bit of a coordination problem. That N2YO website will show you the picture on the left. So that's where it's going. In this case, it's going to go south. And so the way I've done it, I've gone out with my compass and I've said, right, it's going to come up, in this case, at 244 degrees. Find an object. In this case, I've got a picture of a white tree, but something, so you know where it's going to come up. Find out which mountain it's going to be above in the middle, at its highest point, and where it's going to go down. So you know before you start that on the moment it comes up on the horizon, you're pointing over here. Then you follow it over. You know you need to get to the middle at a certain time, and then you need to get down to the other side at a certain time. So work that all out beforehand, so that when it's actually happening, as one less thing you're going to have to worry about what the angles are. I put my watch on the back of my hand, so when I'm holding this like this, I can see my watch, so I know what time it is. I have a headset for my handy, and I have the handy clipped into a pocket or on the shirt. So as you're doing all this, all you have to worry about is pressing the PTT at the right time. So as I said, you're following it along, you're rotating it slightly to get the best signal for the polarization, you're talking to people, you're following it by your landmarks and your watch, and then it goes down the other side. 10 minutes is a good long pass. John will get, how many questions will you get in? 20 questions. So 20 questions to the astronauts would be 20 QSOs for you. So you need to be snappy. You don't have to be ridiculously fast, but you're not going to have discussions about the weather. You want to just get there, talk to somebody, come back. If there's nobody there, which is very unlikely, then you probably saw there is a way of opening the channel, which is a different CTCSS. So you can actually trigger it yourself and then put out a CQ. But particularly things like SO50, there's always seems to be somebody on, so even at that time of the morning. So yeah, that's kind of it. How you do that kind of thing. Then that's kind of the amateur radio side of it. But there's a lot of things that are up there that you can do. And all of what I'm going to talk about now, I've done with a white stick antenna. So ISS does APRS, it does some voice. As John said, they're going to be doing an ARIS contact with a school, where they go to a school, set up all this stuff, and actually talk to the astronauts. It's unlikely that you'll manage to do that, but some people do. As I said, white stick will do. You can even do it with your standard handy with its rubber antenna on it. You can receive some of the digital stuff on the RTLs. You can certainly talk to things like the SSTV and stuff with a handy, if you get it right. There's a bit of a list there of what you can actually use to receive it. It can be done with a handheld next to your Android phone. So the speaker is pointing at the microphone and your phone is running something like Robot 36, and it will receive SSTV pictures from the ISS onto your phone live there and then. It's difficult to do that, but it can be done. If you want something that will track the Doppler for you automatically, plenty of programs out there. This one, WX Track by David Taylor, who I think is still in Edinburgh. It's a very, very good piece of software. It does the same thing as you can see in the middle there. It tells you where everything is. And at the bottom of the screen, you probably can't read it. It's giving you the AOS, LOS, and all that sort of thing. But this will actually work out the Doppler corrections and send it to a program over CAT if you've got a CAT-controlled program. So that's useful for doing things like APRS, the position tracking thing. There's a transponder sometimes on the ISS. Or SSTV, there's a picture that came down a few years back now, 8 years ago, which you can get, again, just from that white stick on the roof or on your car. There's a load of telemetry sats. We have the amateur sat FunQ1, which was, I think it could only be described as remarkable now. When did it go up? 13, November 2013, and it's still working. It's still up there. That is an amateur product. It doesn't have a commercial impact. It's just amateur. And there's others, Naif, Fox. So I think, did Naif go off air? Yeah. But anyway, there are ones up there all the time. Again, you can receive those. There's some pictures of them, and you can get telemetry. It's not a very good slide, I'm afraid, but you can see there's some stuff about voltages, temperatures, all that sort of good stuff that you might be interested in. And this is all can all go back to a warehouse, so that for FunCube we've got some incredibly large amounts of data, because everybody who receives stuff sends what they received back to this warehouse, and that's happening all over the planet. So we've got a very good detailed picture of the whole of the orbit data, and so the opportunities for citizen science there are just huge, and particularly over that length of time, we should be able to learn a lot. And finally, weather satellites. There's a picture of that RTL SDR. This little one is a metal one, so it's slightly better, a little bit more noise interference removal. Now, as you know, a white stick is great for terrestrial, but it receives nothing straight above it. So if you're picking up a weather satellite, you get a straight line just above where you are, where it goes fuzzy and it doesn't work very well. If you get a QFH, John, where's your QFH? Is it here? Okay, anyway, wherever it is, I can't. To my right. Oh, there it is. Gosh, straight. Right, okay, sorry, big dozy. That's actually the wrong frequency, but there's a picture of one there that you can make yourself out of water pipe. Connected up to that Sawbird, which is basically just a preamplifier, and you can get pictures like I've got there, that one in the middle. The outlines and the colours are not real, but all the weather patterns and the shades all are completely real. And that's it. How to do amateur satellites in a rush. In 45 minutes.
Thank you, Heather. That's great, and thank you for standing in for Kieran. I used to do this presentation probably about 10 years ago, as we used to start the colloquium when we were at Guildford, and I was just talking about LEOs at the time. Things have come along a long way since then. About the data warehouse, yes, we've got. We started out with 2,000 ground stations submitting data on and off. She's 10 years old now, so she's not putting out quite so much power. So we're limited to the number of ground stations, and it runs about 35 ground stations regularly sending data across the world. But when Jovian 1 and all the other ones come online, we'll have more opportunities for people to come into it. Any questions for Heather, please? Silence is golden. Your appreciation, please, for Heather. Oh, we have one here.
QO100, how long is it still going to be up there? Any ideas about successors to the Qatari?
I do not know. We haven't heard, I don't think has anybody heard anything about end of lifing?
15 years lifespan, so we're halfway through.
There you go, 15 years, halfway through. But I suspect, I think there is talk about the Americans trying to put something up because they aren't on the footprint. So there's obviously we want some of this as well kind of feelings. So I don't think it'll be long before there's another one up. Yeah, I'm sure we'll be very keen to have something if we do lose Oscar 100.
Any more questions?
Yeah, you just mentioned Q100, so it rang the bell. Are they not preparing another geostationary satellite around region 2? Are you like... anyone's aware of that? Oh.
Yeah, QO100's halfway through its lifespan. There's currently a study being funded by the European Space Agency. They've put in 250,000 euros for a study. The idea is to put a geostationary satellite with a amateur payload. Geostationary satellites are 50 to 100 million. No one's going to fund that for amateur radio. So a payload on board somebody else's at around 47 west is the target. So midway across the Atlantic. It should go almost out to California and back over to Eastern Europe. Study at the moment. Let's hope they fund the real thing.
Any more? We'll try that again. Thank you, Heather.